Hello, dear friends, and welcome to the bias-variance trade-off lesson. It's the one you've been looking for, even if you didn't know that. So in this lesson, we're going to learn about bias-variance trade-off and how you can use them to discuss your model. So bias-variance trade-off, it's basically a fundamentally important of how you're going to understand your model's performance and its evaluation. See, the variance trade-off is the point where we are just adding noise by adding model complexity or flexibility. The training error decreases as it should. Test error starts to go up. So the model after the bias trade-off begins to overfit. So let's go ahead and get into this, and we'll imagine a dartboard. So picture, if you will, that the center of this target, or a dartboard, is a model that perfectly predicts the correct values. And the farther from the target, the worse our predictions will get. We'll go ahead and make a low variance versus a high variance quadrant, and high bias against low bias. And this is a good way to visualize and then understand what bias and variance terms actually means. So imagine if we could repeat our entire model building process to get a series of separate hits on the target. Given the variability of luck in the training data that we collect, each of our fit models represents an individual realization. So sometimes we could get good distribution of training data, so we predict very well and we get close to the target. Sometimes our training data can be full of outliers or non-standard values, resulting in worse predictions. So these different insights result in a series of hits on the target. Or aiming for something, let's say, for low bias and low variance. But what you need to do realistically is trade off variance or bias. And here we can see that a low bias model with low variances in the quarter of the target will predict correct values on the target. The low bias high variance model will predict values around the bullseye, but with a high degree of variance. Versus a high bias low variance model in that lower quadrant, we're going to have a high bias to a certain location, but low variance. So all your model's predictions will be in a certain area. And high bias at the worst high variance means, well, you're basically everywhere. A common attraction for beginners is to constantly add complexity to a model until it fits very well with a training set. But for now, we'll start understanding this in a machine learning algorithm or learning about linear regression. So what you might want to do is suppose that you're given a set of red training data. You are now testing data region training data, okay? Now, you may have a simple model like a blue line, and you get a specific error in your training data, and you decide as a beginner, well, maybe I should make the model more complex or more flexible so that we can get all these training points. However, for hitting all those training points, you're going to your model's going to fail to predict for new test points, which is why we do that train-test split. Doing so can cause a model to overfit your training data and, as I mentioned before, cause major errors in new data, such as the test set. So what we're going to do now is we'll look at an example model of how we can see how overfitting occurs in terms of an error using test data. So what we'll do is use a black curve with some noise points to represent the actual shape the data follows. Okay, so we have three images here. First one is X versus Y. And here we have model flexibility as different linear fits. A linear fit, a quadratic fit, or a curve fitting each becoming more complex, right? So the simplest is just a linear fit. More complicated, quadratic. Then you could have a spline fit. And notice here that the black curve is the truth that the model actually follows. So all the points are just noise around the actual black curve, which is the truth. Now, to evaluate your models and compare the complexities, all you need to do is determine the complexity or flexibility of the model. For instance, the polynomial level of a regression fit versus the error metric, such as mean squared error. Now, as you can see here in the middle plot, we did exactly that. And we plotted for training data versus test data. Now, notice over here to the left, we have a simple model, the yellow linear model. For this model, we have a high error in both test data and training data. And as we get more complex with a blue quadratic model, we begin to reduce the error for test data and training data. But as a result, you start to increase the error in test data, new data. So you want to find the point, you see. This will balance bias with variance. So in this particular case, it's going to be closer to the quadratic fit, the blue point. So you want to balance out the bias and variance of your model to the point where your test data and training data have reached some sort of minimum and grouping together. This is a classic drawing that shows this as a general stance where you have low and high model complexity on the x-axis and some kind of prediction error on the y-axis. And as you move to the left, you get a higher bias but lower variance. And as you move over here to the right, to a higher complexity model, you get a lower bias and a higher variance. So what we want to do is pick a point where you're comfortable with the bias trade-off. You can go to the left of it. You'll start to underfit the data. And then let's go back over to the right. You'll start to overfit the data. So what this means is you're hitting all of those points and your training data and new data is cutting a larger error because of that. Okay? So keep that in mind as we continue using Python for machine learning. Now, of course, this is a bit of that theoretical background. And if you want to look at it more in depth, it's something to keep in mind when you start working with your real world data. All right, my dear friends, thank you, and I'll see you in the next lesson.